Let's talk about nucleophilic substitution reactions and elimination reactions. So in a nucleophilic substitution reaction, we use a nucleophile, a compound that loves the nucleus. In an elimination reaction, we use a base, a compound that has got electrons that can be donated. So because a nucleophile has got lone pairs of electrons and also a base has got lone pairs of electrons, all nucleophiles are potential bases and all bases are potential nucleophiles. So because of this, you are going to see that elimination reactions and substitution reactions are going to happen together. So let's compare SN2 reactions and E2 reactions. Starting with when you have got a primary substrate. A substrate is just a compound that contains the leaving group. So then what is going to happen when you have got a primary substrate? So when you have got a primary substrate and then you are using a strong and unhindered base or unhindered nucleophile, what we mean by unhindered is that it doesn't have a lot of electrons. For example, ethoxide just has not really electrons, but it doesn't have a lot of atoms. And ethoxide only has got two carbons. So then the major product when you have got a primary substrate and then unhindered strong base is going to be a product that is going to come by SN2 reaction. So in SN2 reaction, what you're going to see is that the ethoxide is going to attack the carbon that contains the leaving group from the back direction, and then this bond is going to be broken. So in that case, what you're going to see is that we're going to remain with this carbon, this compound which has got two carbons, and then this oxygen is going to act as a linkage at that position, and then you are going to have this portion of this compound which has got two carbons. We know F just means two carbons, like that. So this will be the product. So in this case, we can see that this is an ether being produced, a ethox ether as a major product. So the major product is going to come by SN2 reaction. Now, SNE2 reaction is able to undergo for or is able to happen for this reaction. Now then, what happens in E2? So the ethoxide, you consider the carbon that is bonded to the alkyl, to the halide or the halogen. Now one carbon away from that carbon bonded to the halogen, you consider the hydrogens on there. One of the hydrogens is going to be grabbed. When it is grabbed, the bond is going to be broken here because carbon is more electronegative than the hydrogen. So it takes up those two electrons. When that happens, this bond will also be broken. So what you just remain with is a compound that contains two carbons. Because this bond is being broken, you are forming another bond, so you are going to have a double bond. So the product will be ethene. Now this one is going to be a minor product. This is going to be the major product. Why? Because we are using a strong unhindered base. It is strong, meaning it can easily attack the carbon that contains the leaving group, and then unhindered, meaning it can easily penetrate and be able to attack. That is why the major product is this one, other than the E2 mechanism. Now, what happens when you get to use a secondary substrate? We are still using the same bases, strong and hindered base, but we are using a secondary substrate. So for a secondary substrate, a strong base, you are going to favor an elimination reaction. Why? Because there is steric hindrance. So if you can look at this position, you have got these carbons, these carbons. So for this to be able to attack and then break this bond, that will not happen easily. So that is why this reaction is going to opt to use the E2 mechanism. So the same ethoxide, of course, can attack this position, and then this bond is going to be broken. And then what are we going to be able to form? We are going to form something like this. We are going to have this O being bonded at this position. And then this is O, of course, with a carbon chain with two carbons. So 1, 2. So this product is coming in by SN2 mechanism. But we know this is not a major product because the major product is supposed to come in by elimination. So what happens then by elimination? the same ethoxide, what is going to happen is one carbon away from this carbon that contains the bromine, any one of those hydrogens is going to be grabbed. So if we grab this hydrogen, this bond is going to be broken, forming a double bond here, and then this bond also end up being broken. So what we are going to be able to see is this compound. And this is going to be the major product. About 79% will be this compound, and then just about 21% will be the one by SN2. For a secondary substrate and a strong base, which is unhindered, the reaction you are going to take is E2. Let's say if we are talking about a tertiary substrate. Now, a tertiary substrate is really hindered. There is a greater steric hindrance, meaning that this carbon which contains the leaving group has been covered, it has been protected. So it will be very hard for you to be able to attack that one. So this makes this reaction never to happen by SN2, because SN2 has to do with the nucleophile attacking the carbon containing the leaving group. Now for a tertiary, this will not happen. Of course, a little product can be seen when the temperature is low. You can see here we are using a lower temperature. So you might see a bit of SN2 product if you are using a lower temperature. What is going to happen? This one will come like this and attack from the back. This bond is going to be broken. So what we are going to see is something like this. And then the ethoxy will join at this position. So this can be a product. But just another thing again is that it will not be the major product. Actually, it will just be about 9% of the product. That is because the temperature is lower and it can support a nucleophilic substitution reaction. But for an elimination reaction, any one carbon away from this carbon that contains the bromine, the hydrogen is going to be grabbed. So this will go and grab the hydrogen, this bond will end up breaking, and that breaks this bond. So what are we going to form? We are going to have a double bond here, and then we have also these two like this. So this is going to be the major product. That is happening by what mechanism? This is happening by E2 mechanism. Now, what if you get to increase the temperature? You can see the temperature is higher by the same reaction. When you increase the temperature, you are just limiting the happening of a nucleophilic substitution reaction. And so the reaction can only happen by elimination. So you'll not even have any product by nucleophilic substitution. So the only product that you're going to be able to see is this one that is coming from elimination. So that will be the only product that is going to be seen only. Okay. Now, how does the size of the base or the nucleophile affect the reaction? So when you are talking about size, you can have the nucleophile or the base being unhindered, meaning small. For example, you can see a methoxide. It is a small nucleophile or base, and at the same time it is also strong. And then you have got a tet butoxide. Tet butoxide is really big, 4 carbons, 1, 2, 3, and 4, and then you have got an oxygen at the end which is negatively charged. So then what is going to happen for these two reactions? So for the first one, where you are using a small base or unhindered base, the major product will be mostly by substitution. You can see this is a primary this is a primary alkyl halide. So meaning it can either happen by SN2 or E2. But because you are using a small unhindered base, this is going to be more by SN2 actually. So what happens is that this base is going to be able to attack this carbon containing the leaving group, and then this is going to be released like that. So what you are going to be able to see is 1, 2, 3, 4. This carbon here, this oxygen will be the point of attachment that will attach at that point. This is a methoxide. I can just put CH3 or I can just put a line like this. It still means that there is a carbon at the end here. So this will be the major product. It is actually 99%. So meaning that this will be the only product, because 1% is too negligible. Now if you use the tet butoxide, this base will be very hard for it to penetrate and attack this carbon that contains the leaving group. So because of that, the reaction will mostly happen by elimination second order. So this is the carbon that contains the bromide. One carbon away, you consider the hydrogen. So hydrogen is going to be grabbed, this bond breaks, and then this bond also end up breaking. So we're going to form this one. So this product will be about 85% being produced. So I mean that it's the major product by what? By E2. And then the minor product, which is the same product which we saw like here, but the only difference is that you don't have an ethoxide but a tet butoxide. I can simply write O and then I'll put a B U with a T, or I can write what Bu with T means. That is a tet butoxide, and the symbol, this is tet butoxide. So this will be a minor product, at least by, if you are using a bulk base and then you are comparing the size of the nucleophile. You can have major and minor. Otherwise, if you are using unhindered base, you only have the product formed by SN being the only product. Now, what if you're talking about the basicity and polarizability of the nucleophile? Then what happens? So comparing the basicity and the polarizability, if you use a strong and slightly polarized base, such as an hydroxide, this hydroxide is really strong. What is going to happen? Hydroxide, another example you can give is an amine or alkoxide. Alkoxide are those which are coming from alcohols. For example, methoxide, ethoxide, tet butoxide. Now, those which you want to mostly use are those which are hindered one. For example, a tet butoxide. That's the one which is hindered. So when you use a strong and slightly polarizable base, that is going to increase the likelihood of an elimination reaction. Elimination reaction, remember, they are good for bases which are what? For bases which are bulky, like the same tet butoxide, or even the same hydroxide and amide. Now, in this example, we have got this one, which is also, this is an acetate ion. It is a strong and slightly polarized base. So what is going to happen in this reaction? What will be the major product? Is it going to be formed by E1, I mean by E2 or SN2? So as we have said, this reaction is going to mostly go by SN2. Okay. Why is it going by SN2? It is just opposite of what we have talked about here. Use of a strong, slightly polarized base such as hydroxide ion, amide ion, or alkoxide, especially the one which is hindered, is going to increase likelihood of elimination. But if you talk about the acetate that we've used in this example here, what is going to happen? This one is weak. This one is weakly basic. And other examples you can talk about are chloride ions, apart from the acetate. So these are weak ones. So these ones increase the likelihood of SN2. So weak bases like chloride and acetate are going to increase SN2. Or even some weak bases which are highly polarizable. For example, bromine, iodide. These are also going to increase the likelihood of this kind of mechanism for SN2. So this one will mostly undergo SN2 reaction like 100%. So what is going to happen? This is going to be able to attack this carbon and then this bond will be broken. And so we are going to have, already I'm going to write this here. We have got like this. and then I'm going to write a connection with this position. I'm going to write it like this oxygen here, and then I'm going to write it like that, and then we have got something on top like that, and then even like this. So this will be the major product, and this is happening by what? By SN2 only. Why is it SN2 only? Because we're using a weakly basic compound. Now, when you are talking about tertiary halides, another thing that you should be able to take note of is that, of course, the reaction mostly competes between, for tertiary, the reaction is going to mostly be competing between E1 and E2. Sorry, not E2, but SN2. For tertiary compounds are better for E1 and SN1. Sorry, this is not a 2, but 1. The reason is for those compounds which are got a lot of groups, ara groups, what you want to do is that this compound first should by itself break off this halogen, forming a carbocation. And then the carbocation can now be attacked via E1 or SN1 like that. So that is why you prefer using that mechanism. The only way if you want to increase elimination product is that you are supposed to use a strong base if you want to increase the elimination product. So then what are we seeing from here? For an E1 reaction, E1 reaction is going to be favored when you use a substrate that forms a stable cation, meaning that tertiary things will always favor E1. Apart from that, a poor nucleophile is going to be able to favor E1. Apart from poor nucleophile, also polar solvent. The polar solvent is used in solvolysis. So that is why it is good for E1 instead of SN1. So where there is a competition between E1 and SN1, if these conditions are met, also increasing the temperature, because basically E reactions work better at higher temperatures than SN reactions. So these are going to be much better. All right. So this is it for this part. Now, as a summary, when you have got a methyl substrate, the reaction is more likely to happen by SN reaction, and that is SN2. So for methyl, it doesn't matter what conditions, it will happen by SN2. And then for a primary substrate, a methyl means you have got a carbon with 3 hydrogens, and then you have got your halogen there. Okay. Now for a primary, you have got a carbon bonded to another carbon, and then this carbon now is the one which contains the halogen. So this one can happen by SN2 or E2. But for it to happen by E2, you need to use a strong hindered base. Because if it is unhindered, for example, CH3 or minus, this one definitely is going to go by SN2. But it should be hindered, for example, tet butoxide, or even this one which has been given here. Another, if you're talking about a secondary substrate, it can happen by SN2 or by E2. Now it will happen by SN2 when you use a weak base, like iodine, cyanide, and also this compound. It will happen by E2 when you use a strong base. So strong bases are going to prefer going by E2 because you know that a base is what is used in elimination. And then a nucleophile is used in what? In nucleophilic substitution. And so every time you increase the strength of the base, just know elimination reactions are going to be more. And then for tertiary substrate, there is no SN reaction, SN2 reaction for tertiary. It can either be SN1 or E1. That is because of solvolysis. So this is supposed to be in solvolysis. Okay. And then you are going to be able to go by E2 mechanism when you use a strong base. So in a case where SN1 and E1 reactions are competing, just use a strong base in a tertiary substrate, then you are going to go by E2 reaction. Let's consider some few practice questions. Give the product that you'd expect to be formed. And in each case, state a mechanism whether it is SN1, SN2, E1, or E2, and then predict the relative amount of each, whether it's going to be the only product, major product, or a minor product. Now, in this one, what are we using? We're using a butoxide. So let's identify what we have, starting with the substrate. The substrate we have here is a primary substrate, and then the base that we have is and this one is hindered. We can see butoxide. It is a very hindered base. So then what mechanism is this going to undergo? Primary and then hindered base. So for primary and hindered base, of course, this is a butoxide. Apart from it being hindered, it is also strong. So this one, the major product is going to be by SN2. Okay. So that would be the major actually the major product will be by E2, because we said that if you have got something bulk as a base, substitution reactions are not good for that. So the major product is that this base will be able to grab any one proton from one carbon away from the carbon that is attached to the leaving group, making this bond to break and then this bond to break. So what we are going to be able to form is this one as a major product. We can also have a minor product because this is a primary substrate. So the minor product is that this same will be able to attack this position and then this bond will be released. So what we're going to be able to see is that we're going to see something like this. The oxygen will attach at this position and then you are going to have this. So this will be another product, but this will be a minor product. Let's consider this one. The same way, but look, the substrate is still primary, but look at the base that we are using. It is strong, but it is unhindered. So for unhindered strong bases, major product will go by SN2 mechanism. And so for SN2, this is going to attack at this position, releasing this. And so what we are going to be able to see is something like this. So this would be the major product. Okay, this is carbon number 1. Number 2 it should be 3 because we have got 1, 2, 3 carbons there. And then we are just having the attachment of the methoxide. Of course, we are going to have a minor product that is going to happen by E2 mechanism. So this is by SN2. By E2, one proton away is going to be grabbed, breaking that bond, and then releasing this compound. So this will be the minor product. Let's consider this one. Let's talk about first the substrate. So the substrate here, you can see this one is attached to 2 other carbons, meaning the substrate is secondary. What of the base that we are using or the nucleophile that we are using? So the nucleophile that we are using here is weak. Okay, this is a weak nucleophile, HS. Of course, it is a, sorry, not weak nucleophile, but it is a weak base. It is a weak base, but it is a strong nucleophile. Why is it a weak base but strong nucleophile? This bond is highly polarized, meaning that these atoms are more like held together because of a high electronegativity difference. Now, the more difficult it is for you to release a proton, the weaker a base you are. So, releasing a proton, of course, is about acidity, not really basicity. Okay. So, it is a strong nucleophile, but a weak base. So, because it's a strong nucleophile, by what mechanism do we expect it to move? It is by SN mechanism. So, the major product will be by SN, and actually it will be the only product. So, what you'll be able to see is that this is going to attack there, this bond is going to be released. So, what we are going to form is this, and then this group, okay, it has been attached. So, because they've specified stereochemistry here, even the stereochemistry of the product is going to be specified. Now the only thing is that for SN2 reaction, there's going to be reverse of stereochemistry. So this Br has been removed. The hydrogen is going to come at this position, and then this other group which is coming is going to attach at this position. So we can see this is position number 1, number 2, number 3. This was S. The product is supposed to be R. Let's consider this one also. So the substrate, we can see this carbon where the bromine is has got 3 more carbons, meaning it is a tertiary. And then the base, we can see it is a strong base. Hydroxide is a strong base. Look at the temperature also. We said if you have got tertiary, temperature will also be important because you can either end up having some elimination reaction, substitution reaction, or only one, depending on the temperature. So you have got a strong base and then tertiary, substrate. Another thing is that we have got high temperature. So by what mechanism is this reaction going to move? So already if you have got high temperature, you don't expect this to move by SN1. We know that for tertiary, supposed to be either SN1 or E1. But because the temperature is high, we have limited already SN1, meaning what remains is E1. But there's going to be a competition between E1 and E2 because we are also able to form E2, especially when we are using a strong base. So because we are using a strong base, the major product is going to come by E2, limiting the E1. If we had used a weak base, we would have formed the major product being from E1 mechanism. So what happens that this OH is going to be able to grab any one proton. This is a carbon, any one carbon away from this carbon which contains the bromine, either this one because they're all the same. So this is grabbed, this bond is broken, and then this bond is also broken. So what we are going to see is a double bond here, and then like that. So this will be the major product coming by what? This is coming by E2. We can have some product being formed by SN1, but as we've said, because we have used a high temperature, that one will be really, really, really small. And also because we have used a strong base, also E1 will be really, really small. Let's consider the last question. So here the substrate is the same, it is tertiary. Now, as we're able to see, we only have the solvent here, and the solvent will be acting at the same time as a base. Now, this solvent, methanol, is it strong or weak? So, methanol here is a weak base. Because it is a weak base, we can already remove E2 from happening. What else? It is a poor nucleophile. And you can also consider the temperature. The temperature is low. So from all of these, poor nucleophile, low temperature. Already because we have got low temperature, we're expecting the reaction also to move by SN1. So because of SN1, we expect that this mechanism is going to be, because of the low temperature, major product is going to be by SN1. Because we're also using a weak base. At least if the base was somehow stronger, the reaction would be more by E1. So then what is going to happen is that this base, now the same solvent we are using as a base, the proton is going to be released. And so this is going to attack this position. And when that happens, now before attacking, remember this is SN1. There's first a spontaneous removal of this bond or the breakage of that bond. So what we're going to have is something like this. This will be positively charged. And then this position now can be attacked. The carbocation can now be attacked by the CH3O minus. This will now come and attach at this position, leading to this compound oxygen and also a methyl at the end. And this one is going to be a minor product. Why? Because this is coming from SN1. Okay, not really minor, but major because it's from SN1 as we already stated here. And then the minor product is going to come from elimination. Any one carbon away, either this one or this one or this one, any one carbon away from this carbon that contains a bromine, hydrogen is going to be grabbed, making the bond to break, forming a double bond there, and then this bond also breaks. So what we're going to be able to form is a double bond at this position. And this one is coming by E1 mechanism. Now really you are not first attacking, it is also in the same vein like this one. First you formed an intermediate, and then this one, instead of it going to attach there, it grabs one proton. It grabs this proton and then this bond is broken. That is how you end up forming this one. You are not attacking first and then you end up with the bond being broken and then the bromine being released. The bromine is first being released, and then after the carbocation intermediate has been formed, your group now attaches at that position.